Hello everyone. Our paper for today, evaluation of influence of AC voltage regulator, SFC and unified power control and, on power losses and voltage quality of asymmetrical distribution system. Authors are Professor Dimitri Ivanovich Pamphilov and Ahmed Mohammed Khouri and Dr. Ahmed El Said El Gibel. Symmetrical loads such as those from railway transport uh, Symmetrical loads such as those from railway transport and electrical drive causes continuous change in power line operation, negative affecting the quality of electrical energy for end consumer. Unbalanced operation also shortens the service life of electrical equipment and load lead to significant distribution feeder losses. Address these solutions. Controllable devices both in power electronic can compensate the negative impact of asymmetrical loads on transmission line operation mode. These devices have a high reliable and fast response and can implement it in a various technology for adaptive control of power transmission line operation modes. It's important to follow IEEE standards and GOST standards to ensure the quality of electrical energy. Our research proposed a methodology to analyze the performance of unbalancing distribution system improved by UPC and SVC and booster devices used to balance the system. An optimization study is conducted to determine the mode of operation of the proposed devices with the objective of minimizing the power losses and unbalancing coefficient. Our paper is consisted of 5 sections after introduction and agenda. The first section introduces the principal operation of the device, and second section introduces the IEEE 13 bus, which is a case study for the unbalancing system, and then the operation scenario, which is an engineered scenario to assess the effect of these devices in IEEE 13 bus. And then the optimal operation of these devices in a system control level, and finally the conclusion of this study. Principle of operation. In this section, we introduce the principle of operation for 3 devices: UPC, SVC, and booster. The UPC is used to balance the reactive and active power in 3 phases, and have 2 modes. We will dive into it in the next slides. And SFC used to compensate the reactive power in the distribution system. The booster is used to regulate the voltage installed at the installed bus. That means it regulates the voltage at the load bus, which used to increase the voltage quality supplied to the bus. The first device is unified power controller, or as a shortened UPC. UPC implemented by a multi-tap transformer controlled by a thyristor bridge. The current produced by this device is approximately pure sinusoidal, which is an advantage of this technology because this technology uses the thyristor as a switches. The number of independent control variables of UPC can differ from 2 to 6, depending the 3-phase transmission line topology and purpose of the balancing. So we have a resilience to implement this UPC in real time, so we can have two variables and then to 6 variables according to the 3-phase or 4-phase or 3-line or 4-line distribution system. Operation scenario in UPC, we have 2 operation scenarios. The first scenario is balancing the active and reactive power by compensating the negative and zero components, and we can also compensate that. We can also change the positive component using passive element, in our cases capacitor, to compensate the reactive power of the load. So we have two operations. The first operation using UPC to balance the active and reactive power, and second operation using to balance the active power and making the reactive power equal to 0. We will go to down that we will say UPC in this mode as UPC SFC device. The second device is SFC model. The SFC model is used in this study to compensate each phase individually due to unbalanced operation of the system. The SFC model in this paper uses the static model, which is suitable for power flow studies. The static model are consisted of 2 buses. The first bus PQ bus and the second bus is PV bus. The booster is a device that uses the series voltage to change the series voltage supplies to the load, so we can control the overall voltage of the load. This injection or subtraction is implemented by thyristor switch, AC voltage regulator, and multi-tap power change. The booster model in power flow study is a PV bus. Our case study, which is used to implement our devices on it, is IEEE 13 bus system with a rated voltage 4.16 kilovolt and net active power 3.4 megawatt and net reactive power 0.3 megawatt. This is the load and branch data, and as well as is shown in the paper, we can see that we have a variety of load model, and we have a single phase loads, and two double phase loads, and three phase loads. And the branch data shown here is taken from the IEEE sources. So we conduct the bar flow study to ensure that we model the system correctly, and we see the flow of the power in the buses. All the buses voltage bar flow study around the unity. That means the bus, even though the system is unbalanced, that means the operational voltage of these buses within the acceptable bounds. And from this study, we can see that 675 bus and 634 buses are heavily loaded, so we will use this fact to install our devices on those buses, and the power losses of the base case is 105 kilowatt. The proposed location and unbalancing ratio. The proposed location according to the load flow study, two buses 634 and 675, which we will indicate it as bus 1 and bus 2. The Neutron used the Neutron unbalancing load flow study is used as a methodology of analysis. In this study, the ratio between the negative and positive component is unbalancing ratio, is a very important factor to look at. The operation scenario, which is a design scenario as mentioned before, the first scenario is the base case, the second scenario the system installed at bus 1, and the second scenario and the third scenario the device is installed at the bus 2, and the third scenario at the same time the device is installed at bus 1 and bus 2. As seen from the unbalancing booster unbalancing ratio, we can see that locally the booster can enhance the unbalanced ratio, but for overall system it is not designed to do such things. And also the power losses when using this device is very high compared to UPC and SFC, and SFC do the same, decreasing the unbalanced ratio locally in the installed bus, because the effect of injector active power, so we didn't have to we decrease the supplied current from the source. But we go to UPC device, we can see that UPC, which is designed to do the same by injecting this asymmetrical component to the system, we can see that it decreases the unbalanced ratio for overall system, and that triggered us to conduct a special study taking into account a system control level to control the UPC and SFC. And also UPC decreases the power losses further more than SFC and the booster. This special study is triggered because of the fact that scenario number 3 is better than scenario number 4, while scenario number 3 used one device and scenario number 4 uses two devices. So we should conduct a special study upon that. As mentioned, UPC have two modes. The first mode, which is compensating the negative and positive, and the second mode, which is compensating negative and zero, and then compensating a part of the positive component, which we declared as a UPC mode 2. And this UPC SFC study, we can see that UPC, when injecting the active power to the system, have more effect on the in terms of unified power, in terms of the unbalancing coefficient and power losses. And see the power losses for all scenario, for all devices that can using UPC and SFC have the less power loss and a higher unbalancing ratio. We found that although the booster enhances the unbalancing ratio on the buses where it is installed, it increases the system power losses significantly. And in other hands, UPC and SFC have a similar results in terms of the power losses, but UPC has an advantage over SFC when it comes to reducing the unbalancing ratio. We also found that adding SFC functionality to existing UPC reduces both power losses and unbalancing ratio. Furthermore, our results show that UPC is a flexible device if used in a system control level, providing further enhancements in terms of reducing power losses and unbalancing ratio. To further illustrate this finding, we conduct a comparison between SFC, UPC, and UPC with a system control level, which will be introduced in the next section. In this section, we will discuss our approach to optimizing the power line operation using UPC devices. We create an optimization problem to find a solution for phases power where the UPC is installed that enhances overall power losses and unbalancing ratio for the system under study. Our optimization is designed to produce a fast solution that can be used by a system operator in real time by decreasing the number of variables to only 2 and limiting the number of stalled generation to 25 out of total 50 generation. The objective of our optimization problem is a multi-objective function that include minimizing power losses and the median of unbalancing coefficient. We also include the equality and inequality constraints in our stats, such as Newton-Raphson constraint regarding power and bus voltages. Our result shows that using or adding system control level functionality enhances the overall power losses and unbalanced ratio by up to 11% compared to using UPC device. When we compare the power losses and balance ratio between the different devices, SFC, UPC, and UPC with GA with genetic algorithm, we found using a combination of UPC and GA provide the best results. This is a power losses showing that UPC GA have a less power losses and a less unbalanced ratio compared to other scenarios from the base case to UPC. In a conclusion, our study assessed the impact of a 3-power electron-based devices on an unbalanced 3-phase system power losses and voltage quality. We propose a mathematical model for these devices for use in a standard IEEE 13 bus system and describe a universal power flow model that allow us to calculate and analyze the operating modes for each device. We evaluate the effectiveness of using these devices in a various locations within the power system to reduce overall losses and improve the electrical energy quality indicators. We formulate an optimization problem to control these devices to achieve integral criteria for electrical energy quality indicators. Our performance evaluation shows that while the booster devices perform the worst using UPC and SFC improves the unbalanced system performance. Compared to the base case, we also found combining UPC and SFC require an optimization study to determine the optimal contribution to this system. Our research shows the optimal operation of these devices reduced total losses by 11% and unbalanced ratio by 39.5 compared to the base case. This research serves as a foundation for implementing these suggested devices in a larger unbalanced 3-phase distribution system. Thank you.